Okay. Hmm. Okay, will you go away? Okay, good. Finally. I hope people can hear me. Okay. Um, Let me just see. Okay. Well, I'll assume that this is recording. Okay, so let me uh, finish sections 8.2, series sequences summation notation. Okay, so I told you what a infinite sequence was. How about a finite sequence? So a finite sequence is just a sequence that contains, well, a finite number of terms, such as 2, 3, 11. And so that would be a finite sequence, just having a few number of terms. Okay, sorry about that. Okay, so let me give you some notation, the summation notation. So suppose I have the following. This is called the um, summation symbol. And it indicates, well, I want to add. And so the sum of the terms. So I can write this sum of terms in, well, a shorter notation. So this is called my dummy index. Sorry. Called the dummy index. And this is my lower. Hmm. My lower limit. This is my upper limit. So this notation here indicates you should add all of these terms starting where you replace your index j by 1, and you keep adding up until you get the uh, last term, which is found by substituting for j n. And so it's just this series here. So let me do an example. Suppose I write the following. Then this indicates the following sum. Replace j by 1, j by 2, j by 3. And that is the sum that it indicates. So a series. A series is just a very special type of sequence. It is a sequence of partial sums. So let's say the partial sums. So suppose you have, let AJ be some series, be a sequence. Then we will construct a sequence of partial sums. Then the sequence of partial sums are the following. So I'll let p sub 1 just be a1. Then let p sub k equal, well, let's say p sub k plus 1 equal pk plus a sub k plus 1. Okay. Then this sequence here is called a sequence of partial sums. And we call that sequence of partial sums a series. So, for example, suppose I have the series let's actually let's say 2, 4, 8, 3. Let this be a series, a sequence. Then we can construct the following series. From it. Okay, so the first term in this Okay. It's sort of stuck for 1 second. Let's see if I can do something. Okay. There. So we can construct the following series. 2. And then we can do 2 plus 4, 6, plus 8, plus 3. It is 2. 2 plus 4. 2 plus 4 plus 8. 2 plus 4 plus 8 plus 3. Okay. We'll usually just indicate this series of partial sums. We'll just identify it by the last term. And so I'll usually just write 2 plus 4 plus 8 plus 3, okay, to indicate the series constructed from a sequence. Let me give you some properties of summation. Let C be some constant. Then the sum of n constants is just C times n. Well, let's show this. So let's use mathematical induction. So let me show the initial case. Okay. And so I just want to show that this works here when n is equal to 1. And so the sum j equaling 1 to 1 of C, well, that's just, you're just adding C one time. Okay. And so, yes, we've shown this. And so, okay. Sorry. Okay, come on. Sorry, I'm not able to write for a second. And so, I've shown that the sum j equaling 1 to n of C is equal to Cn when n is equal to 1. Now let's do the induction case. So let's suppose that this is true for the first k elements. Then we want to show that it's true for the k plus first. So then the sum j equaling 1 to k plus 1 of c, well, by definition, this is just the sum j equaling 1 to n of c plus c. But by the induction hypothesis, we have that this first term here is just, oops, why did I write n? Is just ck. Okay, 1 second. There it is. It's just ck plus the c. Well, this is just equal to c times k plus 1, and that's what you wanted to show. So thus, I've shown that the induction case works, so therefore, by the principle of mathematical induction, the sum j equaling 1 to n of c is equal to cn for all n with c, let's say, some real number. Okay? Obviously, this could be true for C being any sort of member of a field. Next. Sorry. Let's show the following property. The sum. For some reason in the book they write it in functional notation, but of C, let's say A sub j, j equal 1 to n, is equal to C sum j equal 1 to n a sub j. Again, let's show that that's true. Okay. So first I want to show that it's true when n is equal to 1. Well, when n equals 1, this is just C a1. Also, C times the sum j equal 1 to 1 of a sub j is equal to just C1. So therefore, this shows that the sum j equal 1 to n Caj is equal to C sum j equal 1 to n a sub j when n is equal to 1. Good. So that shows the initial case. Oh, I didn't write initial case. 1 second. Let me just pull this down. So initial case. Okay, so that shows the initial case works. Let me do the induction case. So let's suppose that the sum j equal 1 to k for some natural number k, and of course I'm assuming that c and each of these a's are in some field. I'll probably just call it the reals. C a j is equal to c sum j equal 1 to k a j. So let's suppose that's true. Then the sum j equal 1 to k plus 1 of c a j, this is just equal to, well, by definition, the partial sum j equal 1 to k of c a j plus the next term, which is c a k plus 1. So this is equal to, well, by the induction hypothesis, this first term is just c sum j equal 1 to k of a sub j, and so by distributive property, I'm assuming that this is a field, of course. This is just c times sum j equaling 1 to k a sub j plus this last term, ak plus 1. But by the definition of partial series here, partial sums here, we have that this is equal to j equal 1 to k plus 1 a sub j. And so I've shown that the induction step works. So therefore, by the principle of mathematical induction, sum j equal 1 to n of c a j is just equal to c sum j equal 1 to n a sub j. And this is true for all n being a natural number, where c, well, let's just say that these are in fields. And I'm done. Okay. And the next property. The sum rather the next page. So property. J equaling 1 to n aj plus bj is just equal to the sum j equaling 1 to n a sub j plus the sum j equaling 1 to n bj. Okay, where n, of course, is a natural number, and so are the j's, and the a's and b's are in some field. So that's proof. Initial case. Again, let's use mathematical induction. So let's look at the sum j equaling 1 to 1 a sub j plus bj. So this is equal to, well, plug in 1, a sub 1 plus b1. Also, the sum j equaling 1 to 1 of a sub j, that's equal to a1, and the sum, well, that's weird. Okay, come on. Okay, and the sum j equaling 1 to 1 of b sub j, that's just equal to b1. So that shows that the sum j equaling 1 to 1 of a sub j plus sum j equaling 1 to 1 of bj, this is just equal to a1 plus b1. And so these two facts here, well, these are both equal, so therefore this shows that the sum j equaling 1 to n aj plus bj is equal to the sum j equaling 1 to n a sub j plus the sum j equaling 1 to n of b sub j. Okay, so that shows that the initial case holds. Let's do the induction. So let's suppose the following. Suppose that the sum j equaling 1 to k of a sub j bj is equal to the sum j equaling 1 to k aj plus the sum j equals 1 to k bj. Okay, so this implies Well, let's look at what happens for the case. For the case of k plus 1. A sub j plus bj. By definition, this is equal to the sum j equaling 1 to k of aj plus bj plus, so this term, so the kth term plus the k plus first term. By the induction hypothesis, this first quantity here is just equal to the sum j equaling 1 to k a sub j plus the sum j equaling 1 to k bj plus this last term, so ak plus 1 plus bk plus 1. So assuming that this is in a field, that all the a's and b's are in a field, this is equal to the sum j equaling 1 to k a sub j plus a sub k plus 1. Just using the commutative property of addition. And the associative property of addition. Well, by definition of summation, this is just equal to the sum j equaling 1 to k plus 1 a sub j plus the sum j equaling 1 to k plus 1 b sub j. And so that's what I wanted to show. I wanted to show that this property held when I replaced n by k plus 1. And so, therefore, by the principle of mathematical induction, the sum j equal 1 to n aj plus bj is just equal to the sum j equaling 1 to n a sub j plus the sum j come on okay j equaling 1 to n b sub j. And this is true for all n being natural numbers, and for each of these being members of the same field. And that's what I wanted to show. Usually I'll just let the field be a set of real numbers. Next, I'll do that. So let me list these properties, some of which we've already shown. If you add up 1 n times, you get n, which is the first property we showed, except we showed it more generally if the constant was c. Next, j equal 1 to n of j is just equal to n plus 1 over 2. This was shown by Carl Friedrich Gauss when he was 9 years old. He did this. He actually did this like immediately in a classroom. His teacher wanted to, I guess, give them a problem that he didn't think that they could ever solve. So he asked the students to add the sum 1 plus 2 plus 3 plus 4 all the way up to 100. And, well, Carl Friedrich Gauss immediately saw that it was equal to 5,050, just using this sort of idea. Actually, what he did is he looked at the numbers 1 plus 2 all the way to 100, and then he envisioned that you could write them in the descending order, 100 plus 99 plus dot dot dot, all the way down to 1. And if you added those two sums, you'd always get 101. For each of those terms, you get 100 of those. And if you divided that product there by 2, you get 50 times 101, 5,050. Next. Oops, sorry about that. Let's say j squared. Oh, come on. This is equal to n Oh, come on. 2n plus 1 over 6. is equal to n squared, n plus 1 squared over 4. Okay, etc. You can show, of course, each of these can be shown using mathematical induction, but maybe I'll show this using a different technique. So let me maybe just do like one of these, doing it sort of an alternative way. So maybe I'll prove, and I'll just prove maybe the second one. I'll prove the second one using the slightly different technique. So not sort of using the. Well, maybe I'll do the third one. Let me do the third one. Okay. So what I want to do here is I'll use the fact that the first two of these are known to derive the third one. You can then use this technique to use the fact that you know the previous three to divide the fourth, and you can see that actually we'll get a series of different ways of answering I could do the sum j to the fourth, and I can see I'll get a similar sort of formula. Okay, so to prove something involving the square, I'll look at the cube. I'll look at one higher power. And so if you just do a higher power, it'll actually, this trick will help you to solve the next formula. Okay, so let's use the special product formula. So this is just j cubed plus 3j squared plus 3j plus 1 minus your j cubed. And so the j cubes cancel. So this is equal to the sum of 3j squared plus 3j plus 1. Okay. I can simplify this further, but let me leave it at this point for 1 second. So we'll come back to this. Or actually, maybe I should have done it the other way so that I could, well, no matter what way, I have to come back to twice. Okay, so I'll remember this. So now, let me look at this sum a different way. So the sum j equaling 1 to n of j plus 1 cubed minus j cubed. Let's evaluate this. I'll plug in 1. So that's 2 cubed minus 1 cubed. I will evaluate this at 2. So that's 3 cubed minus 2 cubed. At 3, at 4, so I could keep doing that. At n minus 1, at n, and now I notice the following. The 2 cubes cancel, the 3 cubes cancel. So notice that this term here cancels with something that was, well, 1, 2, the third term after it. This term canceled with the 1, 2, the third term after it. This canceled. And so this guy here is going to cancel with, well, if I go 1, 2, 3, cancel with that guy. Similarly, well, this guy here cancel with this one. This one here cancel with something previous to it, 3 previous to it. And so the only things that are left is this one and this one. And so I get, n plus 1 cubed minus 1 cubed. This is what's called a telescoping series. So if you've ever had one of those telescopes that, those old telescopes where they just collapse into a small thing, and then when you want to look out at it, you stretch it out. Or you can think of sometimes when you go camping, you have like a collapsible cup. So it's things that collapse and expand. And so this can be thought of, a telescoping series as something that you just sort of collapse it because a whole bunch of things cancel. Okay, so now I get that, well, n plus 1 cubed minus the 1 cubed is, well, this series is the same as this. I just rewrote it. And so it must equal the sum j equaling 1 to n 3j squared plus 3j plus 1. Okay. And so I have that, well, what's that? N cubed plus 3n squared plus 3n plus 1 minus 1 is equal to, using the properties of summation that we had just shown, well, the sum is linear. It's just 3 sum j equaling 1 to n of j squared plus 3 sum j equaling 1 to n of j plus sum j equaling 1 to n of 1. Okay, so I have n cubed plus 3n squared plus 3n, the ones cancel, equals, well, I don't know what the sum of j squared is. That's what I'm trying to figure out. But I do know the sum of j. So I'm assuming I know this previous formula here and the previous one before. So I'll use them. So this is just equal to n plus 1, and this last sum here is just n. Okay, good. Let's multiply everything here by 2. So I get rid of all the Okay, so let's multiply by 2. And so I get 2 n cubed plus 6 n squared plus 6n is equal to 3 sum j equaling 1 to n of j squared plus 3n squared plus 3n, just multiplying the 3n inside the parentheses, plus, ooh, don't forget to multiply by 2, stupid, 2n. And so, I forgot to multiply the right-hand side by 2. Okay, so those terms. Okay, so now let's subtract 3n squared. Subtract, that's 5n from both sides of my equation. J squared. Good. So I can divide by 6. So that says the sum j equaling 1 to n of j squared is equal to, well, let's just divide by 6. I can factor an n out of this, so it's n 2n squared plus 3n plus 1. But I can factor that last term. And so this is equal to n 2n plus 1 n plus 1 over 6. 2, 3n. Yeah. And, well, that's what we wanted to. Oh, I did want the n plus 1 first. It's, of course, it's commutative. And so that is what we wanted to show. Okay. So you can show all those types of things. Let me do on page 738. Let's do problem number 16. 1, 8, 27, 64. Write the write the next term of each sequence. Oh, okay. So 1 cubed, 1, 2 cubed, 8, 3 cubed, 27, 4 cubed, 64. So 5 cubed is 125. So the next person in this pattern is 125. How about 18? A, AR, AR squared, AR cubed. What's the next term in the sequence? Well, if I look at this pattern here, It's a r to the 0, a r to the 1, a r to the 2, a r to the 3. Well, it's got to be a r to the 4. And that's the next term in this sequence. Let's do the following. How about problem number 30? It says a sub 1 is negative 5. A sub n plus 1 is equal to negative a sub n minus 3. Assume that each sequence is defined recursively, and so this is a recursive definition where the way that I've written this definition here. Find the first 4 terms of each sequence. Okay, well, the first term is negative 5. Let's figure out the second term. Well, it says by this definition here, it says the second term is minus the first term minus 3. And the first term was negative 5. And so I get positive 2. Good. A sub 3, well, that's by definition negative a sub 2 minus 3. So negative 2 minus 3 is negative 5. A sub 4 is equal to negative a sub 3 minus 3. So change the sign so that negative 5 becomes a positive 5 minus 3 is positive 2. Okay. So first 4 terms. Oh, okay. So the first 4 terms of this sequence are negative 5, 2, negative 5, 2. So we probably see a pattern here, just given those first 4 terms in the sequence. Okay. Let me do problem number 37. Negative 1, positive 2, negative 3, etc. Okay. Determine whether each series is an alternating infinite series. So, first, is it an infinite series? Well, yes. And so, it's infinite because of these ellipses here. These ellipses, well, don't have anything on the right. Therefore, it says continue with the same pattern forever. And so this is an infinite series. So, or maybe I should say that this implies infinity. Okay. Next, well, does it alternate? What does it mean to alternate? Well, it alternates if the signs keep changing. And so notice it goes minus, then plus, minus, then plus, and they'll keep alternating. And so notice that this has a negative 1 to the end. So when it is odd, when the if I look at the an odd term, it will be negative because a negative to an odd power is negative, and when it is an even uh, term, then a negative 1 to a even power is positive. And so it alternates between positive and negative. So therefore, this is an alternating infinite series. Which are really weird. So this is a divergent alternating infinite series. Um, so it doesn't have those properties, doesn't have nice properties that we had told you about. Uh, so if you actually regroup terms, you can get differing answers. So if you know, just look at like adding pairwise. Oops, how did that? If you just look at uh, like adding pairwise, then what you'll notice that you'll get some number. You'll get like 1 plus 1 plus 1, okay. But if you say, well, let's take this and then group these two terms together and group pairwise, then you can get a negative. So instead of getting 1 plus 1 plus 1, you'll get a negative 1, minus 1, minus 1, minus. So here it looks like you get infinite number of positive terms. Here it looks like you get infinite number of negative terms. So when you add them, do you get a positive number or a negative number? You don't even know if you get that. So these are kind of weird. Um, so infinite divergence terms series are or I could say are interesting, but they're a little bit above what I can tell you for several reasons. Okay, let me do problem number 42. Oops. 40, 42. Okay, so sum k equaling 3 to 6 of 3k. I'll replace k by 3, 4, 5, 6. So this is equal to um, let's see, that's going to be 20, 30, 45, 54, yes. So if you add up all these numbers, you get 54. Notice that in this case, your lower limit was 3. So your first term involved replacing k here by 3. Okay, good. that really finish? Let's see. Should I do anything else involving series? Oh, well, let me do an example. Let me just do one example here. Let's say you want to evaluate. Some JQ1 to, no, let's go 1,000. So you obviously wouldn't just, um, you know, add up all these just like what I did in the previous example. That would take you literally forever. So what I can do is I can use some of the properties that I've given you to evaluate this. So let me do that. Oh, good. So I have that this is equal to 5 times the sum j equaling 1 to 1,000 of j plus the sum j equaling 1 to 1,000 of 3 good. So this is equal to, well, recall that the sum j equaling 1 to n of j is just n times n plus 1 over 2, and the sum j equaling 1 to n of c is just cn. So this is just 3 times 1,000. And so that'll be 500 times 1,001 plus 3,000. And so that's 500 times 1,001 plus 3,000 is 5,000, 500, 3,500. Okay. So that is a way to compute these using the previous facts that I've given you, using the fact that the summation is linear and that we have these formulas. So I just use these two formulas. Okay, so that finishes off, oops. Okay, let me save this. Okay. Oh, this is still 8. Oh, come on. There it is. Sorry. This was 8.2. Okay, good. Okay. Oh, okay. 1 second. Let me share this next one. This is going to be this guy. Okay, good. Oh, I guess I'll have to go to section 8.6. Permutations and combinations. Okay, so the multiplication principle, for Vince. So suppose, so let E1 and E2 be events with E1 occurring in M different ways, and E2 occurring in N different ways. Then event one followed by event 2 can occur in Mn different ways. Okay. So, for example, if you have, let's say 2 different pairs of shoes, and you have 3 pants, okay, then they can occur in 6 different ways. So then you have 6 different ways of choosing your shoe and pants. Shoe and pant. Okay, so suppose you have shoe 1, so you have one pair of shoes, and you have these. Oh, maybe I should. So I'll start here and I'll say, well, look, I can choose this shoe or that shoe. Now I can choose this pant or this pant or or this pant. Similarly, if the second shoe, I can choose this pant, or this pant. And so that says that I can pick, well, shoe 1 and pant 1, or shoe 1, pant 2, shoe 1, pant 3, shoe 2. Okay, sorry, I can't write as fast or the computer doesn't keep up with me. So I gotta slow down. Okay, shoe 2 with pant 1, shoe 2 with pant 2, or shoe 2 with pant 3. So there are a total of 1, 2, 3, 4, 5, 6 different ways that I could choose between the 2 shoes and the 3 pants. Okay. So there's a total of 6 differing choices of these. Now, a permutation. Okay. Let's see if this will do it. So a permutation. Of K objects out of N objects. Sorry. Is a collection. Oh, come on. Okay. Okay. Okay, there. Is an ordered list of k objects. Okay, come on. Out of the of k, or a list of k objects out of the n objects. The number of different permutations of n well, let's say of k of n distinct objects, taking k at a time, without repetition, is n times n minus 1 times n minus 2 times n minus k plus 1. So this is k objects. So, well, the first time that you're able to choose anything, well, you're able to choose any of those n objects. But since you don't want to repeat, then you can't take the object, the same object you've just chosen. So there's only n minus 1 choices for the next time that you choose. And you keep doing this, and you do this k times. I'll be able to, in the near future, write this in shorthand notation. So let me write this in factorial notation. And then I guess I'll have to explain what that is. Okay. So factorial. I'll define 0 factorial as 1. I'll define k factorial, or let's say n factorial, is equal to n times n minus 1 factorial for n being a natural number. Okay. So that means like 3 factorial is just 3 times 2 factorial. But of course, 2 factorial is 2 times 1 factorial. But of course, 1 factorial is just 1 times 0 factorial. But 0 factorial is 1. So this is just 3 times 2 times 1. So we can think of factorial. 3 factorial is 3 times 2 times 1. Okay. You have the factorial button on your scientific calculator. You also have a NPK or NPR. I should have written it with an R, but an NPR. Oh, I know why I don't use R's. I don't use R's because my R's look like K's. So you have a NPR button on your calculator also. Um, Combinations. Oh, I guess I should tell you that then. In a circle. So in a circular arrangement, there are n minus 1 arrangements. So n minus 1 factorial ways to arrange. Okay, come on. Okay, to arrange in things in a circle. So for example, okay, so for example, how many ways? So how many ways can you arrange let's say 5 seats, 5 people, let's say, to be seated on a circular table. Well, it would just be 5 minus 1, 4 factorial. 4 times 3 times 2 times 1, 24. So there are 24 ways of arranging people, the seating arrangement for people on a for 5 people on a circular table. Okay. Let's do combination. So I did permutation, a combination. Please note the following, which is sort of a bad terminology, which is a permutation is also the ways of arranging k differing objects out of n possible objects. But we'll call other things permutations. Okay, so combination. A combination is almost identical to a permutation. The only difference is that it won't be ordered. So combination. Let's say of k objects. Out of n possible objects. Is a list of arrangements of k objects out of n possible objects. And so the number of these denoted by NCR, or, well, I wrote a K here, NCK, is just n factorial over k factorial n minus k factorial. It is just npk over k factorial. Okay. It is also sometimes denoted by this binomial coefficient. So this is the binomial coefficient, which is to be used when we do the binomial theorem from section, what is it, 8.1. Okay, so Pascal's triangle. So to create Pascal's triangle, let's do the following. We start here with a 1. Try to be symmetric. Let's drop down my 1. 1 plus 1 is 2. Okay. One. 1, 3, 3, 1. 1, 4, 6, 4, 1. 1, 5, 10, 10, 5, 1. So 1, 6, 15. Okay. So the way that we proceed is that we always have ones down here, and then to find the next term, you add the previous two above it. So to figure out 3, you go 1 plus 2 is 3. 2 plus 1 is 3. Drop down the 1. 1 plus 5 is 6. 5 plus 10, 15. 10 plus 10, 20. 10 plus 5, 15. 5 plus 1, 6. Drop down the 1, etc. So this is the way that you proceed to create Pascal's triangle. What you note is the following, is that n can be thought of as going this way. I'm calling it k. K can be thought of as going this way. And so the element here will just be nk. So if you look at the row and the column, so n is the row, k is the column, and that is the value of each of these numbers in Pascal's triangle. So this is nck. So each of these elements are just part of Pascal's triangle. So let's look at uh, 5, 3, or maybe I'll call it 5C3. Either way, it's correct. Okay. Okay, 1 second. Okay. Okay, so let's do 5C3. Well, this is the same as 5 factorial over 3 factorial. 5 minus 3 factorial, which is 5 factorial over 3 factorial times 2 factorial. So I can think of this as being 5 times 4 times 3 times 2 times 1 over 3 factorial, 3 times 2 times 1, 2 factorial, 2 times 1. I can see that these cancel immediately. So another way of, well, thinking about this is it's the number of permutations over the factorial. So I could have just done that. I'll do that in a second. So this is equal to, well, let's see. The 3's cancel. And 4 divided by 2 is 2, so 5 times 2 is 10. Or another way of looking at this, so I got the number 10. I could look at Pascal's triangle. And so start at 0. So start counting at 0, 0, 1, 2, 3, 4, 5. Start counting at 0, 0, 1, 2, 3. Therefore, my answer is 10, because this stands for the binomial coefficient 5C3. Do another example. Okay, so let's compute that. I can think of it as 15p2 over 2 factorial. And so rather than doing the factorials, I can think it's the number of permutations. But the number of permutations was what? Well, it's just 15 times 14 over 2 factorial. So I would start out at 15, write out the next two numbers, so 15, 14, and then divide by 2 factorial. And so 14 divided by 2 is 7 times 15 is 105. Okay. Let's do on page 769. Let me do, 16. C8. Okay. C83. This is actually a weird notation. No one ever uses this notation. It should really read 8C3. Okay, let's compute that. Evaluate each expression. Okay, so let's evaluate that. So this is equal to 8 times 7 times 6 over 3 times 2 times 1, using that trick that I just gave you. So you start out with 8, and then you write the three numbers, and there's the three previous numbers. So, well, three numbers, and multiply each of these previous ones. So 8 times 7 times 6 over 3 factorial. Well, the 6's cancel, so you just get 8 times 7 just get 8 times 7. Okay, and so your answer is 56. We do problem 28. Oops. 100 C99. um, you could evaluate this, but it turns out it's like, pff, wow, that's 100 factorial. I can't even do it on my calculator. Calculator dies. 99 factorial can't do that. But a lot of things actually cancel. It turns out that eventually, and I guess we'll have to show that in a second, that Pascal's triangle is symmetric. And so if you look at Pascal's triangle, notice that the numbers on this side are the same as the numbers on this side. So if you're one away from this, well, you're one away from that, and you have the same answers. And so this is the same as 100C1, but that just says write out one number and divide by 1 factorial. Oh, so the answer is 100. So even though you can't put it on your calculator, you can do it in your head. The 100C99 is just 100. Okay. Of course, if you have the, and you should have the NCR button on your calculator, then you should be able to calculate that. Okay. Let me give you some properties of Pascal's triangle. They'll be kind of useful. Okay, 1 second, I guess. Let me have it think for a while. Okay. Properties of Pascal's triangle. Okay, good. So first, let me say that maybe I'll do this. I'll write each of these, at least for the majority of them, I guess. I'll write this in terms of the binomial coefficients. Okay, so first off, I have that NC0. Okay, let me wait a second while it thinks, because it can't think very fast. Okay, so I have that NC0 is equal to 1 for all n. So let me show this. These are really just going to be computations. Well, this is just n factorial over 0 factorial, n minus 0 factorial. 0 factorial is 1. N factorials cancel, so you get 1. So you're done. Next. Okay. Okay, so this first property says that all of these on the left are 1. The next property will say all these on the right are 1. Well, I can wait 2 minutes and just say that, well, by symmetry, in the first property it works. But let me compute this anyway. N factorial over n factorial n minus n factorial. Well, 0 factorial is 1, the n factorials cancel, and so you're done. 3. NC1 is equal to n. Again, I'm assuming n here is a natural number. So this is equal to n factorial over 1 factorial times n minus 1 factorial. Well, 1 factorial is 1. N factorial is just n times n minus 1 factorial. The n minus 1 factorials cancel. So you're done. Let's show symmetry. So this says that these first terms here are just equal to n. And you can see that. It's 1, 2, 3, 4, except, of course, for the 0 term. Other than that, this tells you what n is. Okay. 4. Symmetry. Oh, maybe I should write it the other way around. So NCK is the same as NC n minus k. So let's look at NC n minus k. This is just n factorial by definition over n minus k factorial times. Oh, okay. So this is just n factorial over n minus k factorial times n minus n minus n minus k factorial. And so this is n factorial over n minus k factorial. N's cancel, and so I just have k factorial. Of course, minus a negative is a plus. And well, I can write this as k factorial n minus k factorial. And so this is just equal to in ck. So I'm done. So symmetric. That means that if I look at Pascal's triangle, the right-hand side is a mirror image of the left-hand side. Next, let's show that the way that you obtain a value in Pascal's triangle is you just add the ones above it. So I have that nck minus 1 plus nck is just n plus 1 ck. So let's show this. nck minus 1 plus nck is equal to, by definition, n factorial over k minus 1 factorial times n minus k minus 1 factorial plus n factorial over k factorial n minus k factorial. So this is equal to, well, the way to add these is to get a common denominator. Well, let me simplify this first. Maybe I'll write this as n plus 1 minus k factorial. So I want to get a common denominator here. So I notice that this is the same as this if I multiply this guy by k. So let's multiply, let's multiply by k. And this will be the same as that if I multiply this guy by n plus 1 minus k. So let's do that. Okay. So I have, well, this is just k factorial on the bottom. And this is n plus 1 minus k factorial on the bottom. This is just n factorial times k. Whereas this is just, well, multiplying the n factorial inside, I get n plus 1 times n factorial, which is n plus 1 factorial, minus, well, n factorial times k. The n factorial times k's cancel. So you just get n plus 1 factorial over k factorial times n plus 1 minus k factorial. But this is just n plus 1 ck. And that's what you wanted to show. So, yes, that's how we add. these things in the Pascal's triangle. Next, let me show you how to multiply. Oh, and maybe I'll do this in terms of the other notation. Let me show you how to multiply permutations and combinations. So RPK times NCR Okay, let's see. Maybe I have to move. Oh, this is not disappearing. Okay. Um, One second. Why is that? Is it still doing it? Pause here. No, it should be going. Okay. That should be fine now. So RPK times N. I guess I'll have to use R's. I don't like. My R's look kind of bad, but I'll use an R. Is equal to NPK times N minus K CR minus K. Okay, so let me show that. So R, that's not an R, that's an N. No, that isn't. Okay, that's an R. Okay, RPK. Okay, so RPK times NCR is equal to, okay, RPK is R factorial over R minus K factorial. Here we're assuming that one is less than or equal to, let's see, this is going to be K is smaller. So R minus K is positive. Yeah, so we're assuming the following times N factorial over R factorial N minus R factorial. Okay, good. So one of the things that you notice here is that, straight off the bat, the R factorials cancel. So you get that this is equal to N factorial over R minus K factorial times N minus R factorial. Okay, good. Let me write this as a product of two things. So you want to write this as for N minus K So let's write this as n factorial over n minus k factorial. Well, then I need a n minus k factorial here. Okay, that's fine. And then what remains is, well, n minus r factorial times r minus k factorial. Okay, so this first term is, well, the term we want for NPK. The second term is almost what we want. I just have to rewrite it slightly. Oh, actually, I should have written the r minus k first. I wrote it in the wrong order. Not that it really matters, but r minus k factorial times n minus r factorial. Writing this way will only give me one little step and then we'll be done. So this is equal to n factorial over n minus k factorial times n minus k factorial over r minus k factorial times, well, subtract k from both n and r. That won't change the difference, but now this is equal to npk, and this is equal to n minus k c r minus k. And that's what you wanted to show. Okay. Note the following. I guess I should note n minus k minus r minus k is equal to n minus k minus r plus k n minus r. So that's how I went from here to here with that little note. Okay, so that tells you how to multiply to a permutation and a combination. It turns out that actually this is important for, especially for if you do k equaling 1 and 2 are quite important. So maybe I'll write them. Note, if I wrote this for k equaling 1, in the above. It gives me r in CR is equal to n minus 1, r minus 1. And if k equals 2, it gives me r minus 1 in CR equaling n minus 1, n minus 2, CR minus 2. And those will be very important properties. Oh, and I guess I can't show you that one. Okay. So maybe that's all I want to show you for this. Okay. So this is 8.6. Okay. Okay. 0.6. I guess 8.1 then. Okay, so that can actually give me, okay, 1 second. Let me give you back this. Okay. So section, let me just, okay. Section 8.1. The binomial theorem. So, oh darn, I was going to say, if you look in your book, they actually have done a better job than I have, than I'll be able to do. Okay, if I look at a plus b to the 0, that's 1. A plus b to the first, that's equal to, oh, maybe I should say, well, I'll put those later. That's equal to a plus b. A plus b squared is a squared. A squared plus 2ab plus b squared. A plus b cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed. Okay. Now, let me fill this in a little bit. Let me put in ones here in front of each of these. Now, if you look 1, 1, 1, 1, 2, 3, 3, this is Pascal's triangle. So those coefficients are just Pascal's triangle. Now let me put in some others. A to the 0, b to the 0. Obviously, that's just a 1. A to the 1, b to the 0. Well, that's just, oops, I should have put the 1 over here. 1. That's just a to the 0, b to the 1, that's just b. Well, multiply this by b to the 0. You haven't done anything. Maybe I'll call those a to the 1s. Let's see, a to the 0, again, haven't multiplied by anything. b to the 0, that's just 1. And b, let's write that as b to the 1. Let's write this as a to the 1. And let's multiply by a to the 0. So now what you notice is that, well, 0 plus 0 is 0. 1 plus 0 is 1. 0 plus 1 is 1. So notice that the sum of each of these exponents is just equal to this exponent. Next, the coefficients here are just the coefficients of Pascal's triangle. And so if I wanted to, so this is, Pascal's triangle. So now, if I wanted to do a plus b to the 4th, well, I can figure it out. It's got to be the rest of Pascal's triangle, so it's got to be a 1. And then they said start with a to the 4th, and then you put b to the 0. Then this has got to be, well, let's see, 1 plus 3 is 4, a to the 3, b to the 1, plus, well, 3 plus 3 is 6, a to the 2, b to the 2, 2 plus 2 is 4, plus 3 plus 1 is 4, a to the, well, we started at 4, 3, 2, so this is a to the 1, b to the 3, 1 plus 3 is 4, plus, bring down the 1, a to the 0, b to the 4, etc. Etc. here. Oh, which means I'm able to determine each of these using Pascal's triangle. But if you recall, the members of Pascal's triangle were just these NCKs, which were the binomial coefficients. There's a reason they call them binomial coefficients. Okay. So as a matter of fact, let me, well, maybe in a second I'll write that. So let me, oh, I see. Here's where they put the factorials. Let me write Pascal's triangle, the binomial formula. Which is, I'll do in terms of a's and b's. A plus b to the n is the sum, k equaling 0 to n, just what we've done here, of, well, the member of Pascal's triangle, which is just nck, times a to the, well, n minus k times b to the k. And that's just each of these members here. Okay. And this is for n being some natural number. So let's let's prove this, and then maybe I'll maybe I'll prove this first, and then I'll okay. So proof. Then I'll extend this, and then we'll do some examples. So first, I'm going to prove this by induction. Okay. And I guess here we're actually either, so I should maybe say something about this notation here. So we can either assume that A and B are never 0, or if a is 0 or if b is 0, then 0 to the power 0 is either 0 or 1, however you want to choose it, so it makes the formula correct. So either assume that a and b is not 0, or you have to make some sort of weird assumption on what the notation means. Okay, so I'll sort of say, well, I won't write that down. Okay, so let's do in the initial case. Okay. So first, let's see if this formula is true. When, oh, it's not. I can actually do it for 0. So I can actually do this. Let's say that, uh, well, a plus b the 0. Uh, if it's a non-zero, then it's 1. And if it is 0, then you just make it 1. So you just say 0, 0 is 1. So formulas works. Okay, next. Let's check if this gives me the correct answer. A to the 0 minus k, b to the k. Well, you just plug in 0, so that's 0. That's a to the 0. That's b to the 0. 0 C 0 just 1 by the properties we gave you for Pascal's triangle. A to the 0, b to the 0, again, those are 1. Again, if a is not 0, then any non-zeros to the power 0 is 1. And if a is 0, you just define it as equal to 1. And same for b. Okay, good. So that says that these are equal. So the formula works when n is equal to 0. Let's do the induction step. Oh, wouldn't you know, I used k. Maybe then I used a different dummy index. I used j. Okay, so assume that the formula works for j equaling 0 to k of ncj a what in the world? Please. Okay, what in the world? A n minus j b j. So let's assume that this is equal to a plus b to the k. Okay, so now I want to look at a plus b to the k plus 1. Let's see if it's equal to this formula where I replace n. What in the world? Where I replace n by k plus 1. There was a whole bunch of typos there. Okay, so this is the same as, well, a plus b times a plus b to the k. Okay. Which is equal to a plus b. A plus b to the k is the sum j equaling 0 to k of kcj a to the k minus j b j. Okay, good. So this is equal to, let me just multiply the a and b inside the parentheses, or let's multiply the summation inside the parentheses. So this is the sum j equaling 0 to k kcj a to the, well, I'm multiplying a times this, so I add exponents, so it's k plus 1 minus j bj plus, well, let's multiply b inside the parentheses. So it's the sum j equaling 0 to k of kcj a to the k minus j b to the, again, I'm just multiplying, so I add exponents. B to j plus 1. Okay, good. So now let me just write out the first term here. So letting j equals 0, I get k0 a to the k plus 1 minus 0 b to the 0 plus, well, the rest of the sum j equaling 1 to k kj a k plus 1 minus j bj. So that's this first term where I've written out the very first term. Let's do the same sort of thing, except let me write out the last term. The reason for that is that I want to then write these two middle things without the first and last terms as something that I can write from above, that I can sort of simplify and then see that it works. Okay, so this is equal to the sum j equaling 0 to, well, not the last term, so k minus 1 of k cj a k cj a to the k minus j b to the j plus 1 plus the last term. So plus k k ck of a to the k minus k b to the k plus 1. So let me just write this. So kc0, well, that's 1. B to the 0, well, that's 1. And so this is just a to the k plus 1. So that's my first term. My last term, I'm also just going to write as b to the k plus 1. So this is the sum. J equaling 1 to k kj a to the k plus 1 minus j bj plus. Okay, so now for this one, let me do some change of variable. Let's add 1 to this. So j, k, maybe I'll add I. So I'm going to rewrite this. So I'm going to let I equal j plus 1. So when j is 0, I is 1. And when j is k minus 1, I is just k. And so j is just I minus 1. And j is just I minus 1. So this is k minus I minus 1. And j plus 1 is just I, plus the very last term. And we said, well, let's just write that last term as b to the k plus 1. So this is equal to ak plus 1 plus sum j equaling 1 to k of kj a to the k plus 1 minus j bj plus sum. Rather than calling it I, I'll just call this dummy index j. It doesn't really matter what I call it. And so this is k to the j minus 1. So k c j minus 1. A, well, I have a minus I minus 1. So that's the same as minus I plus 1. So there's a to the k. Let's write the 1 first. Minus I b j. Oh, bj. I'm writing it as j's. Plus b to the k plus 1. So this is equal to, your screen is paused. Why is it paused? Okay, let's come back to the regular. Okay, it's no longer paused. Okay, so this is equal to AK plus 1 plus. Well, notice that this is J equaling K. J is equal to 1 to K for both of these. And I have A to the power K plus 1 minus J and BJ. So this is just KJ plus KJ minus 1, A to the K plus 1 minus J, BJ. So this is equal to well, by the properties of Pascal's triangle, we just did this. That's the way that you compute your element in Pascal's triangle. You just add the 2 above it. So this is just K plus 1 CJ. Okay, good. Had to plug that in. And this is A to the K plus 1 minus J, BJ. And this is plus BK plus 1. Now, actually, let me give this a little room here. I know that K plus 1 to the 0 is just 1. And space over here too. I know that K plus 1, CK plus 1 is just 1. And A to the 0 is just 1. And oops. Let's see if I can get a little bit more of those to move this over. Okay, it doesn't matter. I'll just move this over anyway. And oops. And I also know that B to the 0 is 1. So, putting those in there, I see that this is just the sum J equaling 0 to K plus 1 of K plus 1 CJ A to the K plus 1 minus J B to the J. Oh, I guess I should say here then minus 0, B0. So notice that obviously the first term when j is 0, well, I plug in a 0 here, that's this term. Plug in a 0 here, that's this term. Plug in a 0 here, that's that term. For j's from 1 to k, well, I've just written that. That's the same thing here. For j equaling k plus 1, well, this is this term. And this is, oh, I should have written this as, so 0 is k plus, I guess I'll need a little more space here. So k plus 1, ck plus 1. We know that that's 1. A to the 0, which is k plus 1 minus k plus 1. Well, that's 0. And lastly, we have this term. B to the k plus 1. So if I replace j by k plus 1, I get, well, this term. And then replace j by k plus 1, I get this term. Replace j by k plus 1 is this term. And so I've shown that if I replace n by k plus 1, it also works, this formula. So I've shown that the induction step works. So therefore, by the principle of mathematical induction, this formula works for all n. So therefore, by the principle of mathematical induction, a plus b to the n is equal to the sum j equaling 0 to n in Cj, a to the n minus j, b to the j, and this is true for all whole numbers n. So I'm done. Okay, good. Note the following. So note, if I let this notation be the n minus 1, n minus 2, n minus k plus 1 over k factorial, which is the way I sort of defined, the way I defined it originally. Then we actually have this formula this works for all real numbers. So, and of course, if n is a whole number, then these terms here are going to, these binomial coefficients are going to be 0 after n plus 1 terms. So it is the above formula that we have for the case of whole numbers. Okay, good. So let me, I guess maybe I'll do some examples first. On page 729, let me do Problem number, I don't know, 14. That's a weird problem. 5 factorial minus 2 factorial. Well, 5 factorial, 5, 4, 3, 2, 1. 2 factorial, 2. So I'll give you 20, 120. So 5 factorial is 120 minus 2 is 118. Okay. Let me do problem number 21. It says a plus b to the fifth. Use Pascal's triangle to expand this. So let's write out the Pascal's triangle. So if I do that here, it's 1, 2, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1. And so by Pascal's triangle, I look at this last guy here. It is 1 a to the fifth plus 5 a to the fourth b to the first plus 5 a to the third b to the second. Oh, wait. I missed the 10. Plus 10 a to the third b to the second plus 10 a to the second b to the third plus 5 a to the first b to the fourth plus 1 b to the a to the 0 b to the fifth. And that is your expansion using Pascal's triangle. Let me do problem number 29. And so it says 2x plus y to the, okay, warning, okay. Uh-oh. I am plugged into, okay. So 2x plus y to the third. Use binomial theorem to expand each binomial. So this is the sum, j equaling 0 to 3 of 3j, 2x to the 3 minus j, y to the j. Okay, so this is equal to 30, 2x to the 3, y to the 0, plus 31, 2x to the 2, y to the 1, plus 3, c2, 2x to the 1, y to the 2, plus 3c3, 2x to the 0, y to the 3. Okay, so 3c is 0. That's just 1. 2 cubed is 8. X cubed is x cubed. Y to the 0 is 1. 3c1 is 3. 2 squared is 4. X squared is x squared. 3c2 is 3. 2x to the first is 2x. Y squared is y squared. 3c3 is 1. 2x to the 0, that's 1. Y cubed is just y cubed. And so I get 8x cubed plus 12x squared y plus 6xy squared plus y cubed. And that is your answer. Let me do problem number 40. X plus 1/2 y to the 4th. Okay, so this is going to equal the sum j equaling 0 to 4, 4 cj x to the 4 minus j y over 2 to the j. So this is equal to 4c0 x to the 4 y halves to the 0 plus 4c1 x to the 4 minus 1 is 3 y halves to the first plus 4c2 x to the 4 minus 2 is 2 y halves to the 2. Notice I'm just doing 4 minus 1 is 3, and I put whatever is here up here. Plus 4c3, and then 0, 1, 2, 3. X 4 minus 3 is 1. Y halves to the 3 plus 4c3 x to the 4 minus 4 is 0, y halves to the power 4. So this is equal to 1 times x to the 4th, y to the 0, y over 2 to the 0 is just 1. 4c1, well, that's just 4, x cubed y halves to the first is just y halves, plus 4c2, that's equal to 6 x squared. Y over 2 squared is just y squared over 4 plus 4c3 is 4. X to the first is x. Y cubed over y over 2 cubed is y cubed over 8 plus 4c4 is 1. X to the 0 is 1. Y over 2 to the 4th is y to the 4th. Over 16. So this is equal to x to the 4 plus 4 divided by 2 is 2, x cubed y plus 6 over 4 is 3 halves, x squared y squared plus 4 divided by 8 is 1 half, x y cubed plus 1/16 y to the 4. And that is your expansion. Okay. And so, let's do problem number 50. A minus rad 3 to the power 8, and it's asking for the third term. Okay, so find the required term in each binomial expansion. Okay, so let's do that. Please note, by the way, if you ever take statistics, they do the binomial expansion in the other direction. So rather than going left to right, they write it right to left. So this would be the fifth term if you're doing statistics, not the third term if you're doing mathematics. Okay, so let's do the third term. So notice the following. Let's look above. The first term, well, look, it's a 0. Second term, third term, fourth term, fifth term. So each of these, well, they start counting at 0 rather than 1. So the third term, 1, 2, 3, actually has a j value equaling 2. So this is really going to be, well, 8c2 a to the, well, let's see. Remember I said I'll just subtract 8 minus 2 is 6. Then minus rad 3 to the, well, whatever is here, which is a 2. So all I have to do is figure out 8c2. Well, that should be easy. That's 8 times 7 divided by 2, factorial, which is 2. So that's 4 times 7. That's what, 28? A to the 6. The square gets rid of the square root, and the minuses cancel. So that's just a 3. And so 3 times 28 is 84. And so the third term in this expansion is 84a to the 6. Okay, good. Let's do problem number 58. So a minus b to the power n is asking for the fifth term. And so let's find the fifth term here. So we have an n, and again we start counting as 0. So 0, 1, 2, 3, 4. That's the fifth term, 4. And so a to the power, well, n minus 4. B to the power, well, I'm sorry, minus b, because there's a minus in front of that b, minus b to the power 4. Maybe I'll get rid of the minus here. So this is n c4, a to the n minus 4, b to the 4. That is the fifth term in the binomial expansion. Okay, so that really finishes off section 15, section 15, section 8.1. And so that finishes off, I guess, what we're doing today. And then on Tuesday, we'll finish the rest of this. There's only like 2 sections left, right? Yeah, just 2 sections left. Okay. So that's it. Let me save this. Okay. I'm only at 3%. Okay. Oh. Where's my... Kamista?